Hi all, Dr. Metter here. Let's talk about calculating energy. We've already talked about what types of energy there are. We've talked about in general terms, how do we describe a system with energy? And now we're going to talk about how do you actually put numbers to the different types of energies. So we can define our potential energy as a mass in a gravitational field at a certain height. Okay, as we said before, we set a reference point, and this height from that reference point gives us our gravitational potential energy that's stored in the object. All right, kinetic energy isn't quite as straightforward, but it's 1/2, okay, times the mass of an object that is in motion, that has velocity squared. So kinetic energy is equal to 1/2 mv squared. We can also calculate our elastic potential energy. And again, not as straightforward, but it makes sense what it's based on, as 1/2 K, which is our spring constant, times X, which is our distance from equilibrium. Okay, so basically X describes how much our spring is extended or compressed squared. So our elastic potential energy is equal to 1/2 kx squared. All right, so we can also define work. Work is equal to, remember, it's specifically in positive physics, it's energy being added into the system or work being done on the system. So the force applied to the system times the distance that the mass goes. Okay, our thermal energy, and remember that's the heat loss due to friction or drag, so we can define it as our force of friction, whether that be friction or drag, times our distance of our cart or our object. All right, let's look at an example that puts it all together. All right, so we want to find the velocity at point B, and I'll talk about what point B means. This is our information. So we have a cart on a hill like we've seen before. This is point A, and the cart travels to point B. Okay, and at point B, it reaches the reference point of 0, right? So that cart starts H from reference point. That's some height from our reference point that we set. All right, what do we know about this system? Well, I'm giving you this. Okay, so that we have a drag that's equal to 100 newtons. We have a distance down the hill that the cart goes of 80 meters. And the mass of the cart is equal to 40 kilograms. We also have a motor that pushes the cart with 150 Newton force. All right. Okay, what do we know about this system? Well, we know that our gravitational potential energy up here is not equal to 0, right? It's equal to something that we can calculate. And we know that in terms of general terms, it's equal to our mass times our gravity times our height. All of those we have, because this is given, sorry, forgot to give you this, 25 meters. So we can calculate that. We know that our kinetic energy is equal to 0. We know that as we go down, our work, right, there's work done because we have a motor that pushes. And in general terms, that work is equal to our force applied, right, times the distance it goes. So there's our distance, and this is our force applied. All right, we know as we go down, this obviously has, oh, it's not friction, it's actually drag, so it has some wind that's pushing against it. So we can determine our thermal energy that's opposing motion as, let's see, the force of drag times the distance we're going, which we know is 80 meters. All right, now at the bottom, we know that our potential energy is now 0. All of that energy that was stored is now converted into kinetic energy which is now something, and we can define it as 1/2 mv squared. And there, hidden in our kinetic energy, is that velocity that we're trying to solve for. All right. So if we can get at what this kinetic energy is, we know the mass and we can solve for our velocity. All right. Let me see if I can move this screen real quick. Okay, so let's go ahead and calculate all our different energies so that we can get at what this kinetic energy is. Oops, didn't mean to erase that. So we can get at what this kinetic energy is equal to. Okay, so we know that our potential energy is equal to mgh, which is equal to 40 times 10 times 25, which is equal to 10,000 joules. It's energy, joules. Our loss of energy, or of thermal energy, is equal to the force of drag that's been applied times the distance we go through, which is 80 meters. So our force of drag is 100 newtons times 80 meters. So that's equal to 8,000 joules. We can determine our work that's being done on the system, and this is what's added, the energy that's added to the system, by multiplying our force that's applied times the distance, and that's the force that's applied by the motor. So that's 150 newtons times 80 meters. So that's equal to 12,000 joules. And now, if we want to get at what kinetic energy is, we know it's 1/2 mv squared. We have the mass, so now we need to calculate the velocity. We can use all of these energies because we can define kinetic energy in terms of these energies, as well as 1/2 is equal to 1/2 mv squared. So we can say that this kinetic energy is, in terms of other energetic terms, is equal to the potential energy that's been stored, okay, plus the work that's being done on the system, so that's adding energy to the system, minus the thermal energy that's being lost as heat due to the drag on the system, okay? And that is equal to our kinetic energy. We have all of these terms, so now we can figure out what kinetic energy is, and then we can solve for velocity. All right, so we know this is 10,000 joules plus 12,000 joules minus 8,000 joules, which is equal to kinetic energy. So 14,000 joules is Ke. So we can say that this is equal to 1/2 mv squared. So we have 14,000 joules is equal to 1/2 our mass, which is 40 kilograms, times v squared. And we end up getting a velocity that's equal to 26.5 meters per second. Okay, so we have found the velocity of the cart at point B. So that's the velocity of the cart right here at point B, using our energetic terms and how they transfer from one type to another right here, and calculating each terms with their mathematical equations. All right, let me know if you have questions. I'm super excited about energy. I really like this unit. I hope you guys too. Talk to you soon. Bye.